All right, guys. We've been told we can start, so we'll just start. So basically, who the hell we are? We're like from No Foundation, and what we're going to show now is, well, let's say it this way. It's the way to prove heavy computations to StarkNet and to ETH from mainstream languages without, let's say it this way, without proof generation performance issues. Yeah, that's triggering. Our folks have been hidden after this table. So yeah, this is basically what it is. Let's like why, what for, and shit, who did that? Anyway, why do we need this, right? Well, basically, why do we need this kind of proving Rust or like CPP or anything, like proving computations in Rust and CPP or anything? Why do we need this? Well, basically, let's say it this way. Like actual applications need taxes, dy dx, all right? For example, they require like scalability. And obviously, this scalability requires like a lot of data and computations. Well, that's true as well. And basically, computations, when I'm talking about computations, I'm talking about computations, continuous computations. Not like computations which can be done inside the virtual machines or like anything like this, like EVMs or like anything like this. But it's about continuous computations like ML stuff or like consensus proofs or like zkVM proving or like anything like this, like EVMs, whatever, CaIRO-VM, like RISC-V VMs, whatever. And all of that, if such fellas, if fellas using this want to use this inside a protocol, it has to be proven to a protocol. So you have to like be able to access the data of this, access the result of this, like within the protocol, within some particular protocol. So basically, that's why we need like proof-based compression. So that's pretty obvious. That's exactly the same thing how StarkNet works. It's basically, it just compresses the data, pushes it to ETH. The quality over compressions determines the size of a data, the amount of data you can put in ETH or like something like this. That's like obvious thing. Next thing, well, let's say it this way, it's consensus proofs. It's just an example, okay? It's like what folks have started calling zkBridges some time ago. It wasn't initially zkBridges. Ahat will not let us lie. It was initially like trustless bridges, but then folks have started calling the zkBridges. So okay, it was accidentally. We invented that accidentally. We didn't want that. So basically, consensus proofs for zkBridging are, let's say it this way, time consuming. This is a lot of continuous computations, and that's the first thing. And the second thing, defining consensus proofs in like CaIRO or like in custom language or in anything like this, often time consuming. Well, it's just a huge time to market, and sometimes there is no necessary cryptography primitives. So it's easier to simply like compile the code which is already like implemented in the mainstream language and prove it, and that would be like fine. So, but yeah, so well, basically that's what I just meant. So designing circuits is hard. Sometimes you don't have necessary primitives, and so that's why it makes sense to use like mainstream languages. And well, for example, yeah, designing, for example, Solana's consensus proofs took us something about 8 months for manual circuit design. So that's kind of like Splunkish circuit design, but anyway. And generating proofs, like consensus proofs, again, it's just an example, is hard as well. So I mean, some folks are trying to do that on the local machine. Some folks are trying to like outsource that, and some folks do things like we did. So what is the thing we brought as a solution to all this is basically we designed and brought the thing which we call zkLLVM stuff, zkLLVM compiler. What is that? It's not, well, first of all, it's not a zkVM. It's just a compiler. Well, basically, just to understand the difference, zkVMs are basically, well, just a huge circuits, right? Just huge circuits which define some particular CPU architecture. In our case, I don't know if any from RISC-0 folks have came in here. Hey, nice to see you. It's like basically, in our case, we do not have like a unified VM circuit or anything like this. We propose to generate these circuits from high-level languages. So basically, each time, each new computation produces a new circuit, which is specific to a particular set of to a particular set of logic. So that like reduces the overhead. That allows to prove like really huge logic. That allows to prove like really a lot. Let's say this way, a lot. Like as I said, for example, 4,000 DDSA signatures is doable, and like that's like Solana's consensus proof. In case of our like Mina consensus proof, that was something about 35 billion scholar multiplications. So that's quite a lot. And well, proof generation. What the hell we do with proof generation? Proof generation, well, the larger, it's like the more you prove, the harder it is, right? Yeah. So basically, for all of this stuff, well, you need to either have a really badass local machine, or you need to simply outsource that, and well, to those who do that professionally. So that's what we did. We kind of built a decentralized proof market thing, which allows those who generate proofs to come in to generate proofs, which will be verifiable on EVM and on StarkNet. So, well, yeah, that's what it is. It's like there will be two sections about each of these things, like zkLLVM and proof in the proof market thing, like from our team heads who are responsible for this, and well, they'll do a little bit of a show and tell in like more details about each of these things. Yeah, it's like go on.
Yeah, hi. So I will tell about the zkLLVM and about the toolchain we use. Let's start. Oh, okay. Recently, we designed two zkBridges, one for Solana and one for Mina. And each one of them requires to generate a huge circuit of the consensus protocol of each of the clusters. And with each of them, we have two pretty huge problems. One is that we need to reduce the prover time, and the other one is that we want to control the costs of on the verifier side. That's basically why we decided to design the zk-SnarkProof system, which we call placeholder. This is basically Fry-based, LPC-based Plonk arithmetization. This is a Fry-based zk-SNARK system with Plonk with custom gate arithmetization, and the key features we wanted and the key features we achieved with it is that we can we have pretty flexible parameters. We can adjust them for the target we want for the target environment for the prover, for the target environment for the verifier. We can adjust it for particular prover time, proof size, verifier costs, everything. Yeah, and after we made our proof system, the second huge task for building the bridges was to build the circuit itself. And with building circuit, there are different tools, and we have checked pretty lot of them. And one of the best solutions to use is to use the zkVM. For that time when we started, it was like that. This is basically the zkVM pipeline, more or less in general. But when we tried to use zkVM, we understood that there is a problem Mike told about. It's a problem that the zkVM circuit, this is a circuit which is put it in the proof system after the execution of zkVM. It contains a lot of additional stuff, a lot of constraints which represent the logic of the virtual machine, and that's why even a pretty simple logic requires to add a lot of constraints to the circuit, and that's why the size of the circuit, the size of the the size of the circuit is pretty big, and that's why obviously the size of the proof and the costs on the verifier side, they skyrocketed. So we understood the problem. We understood that we want to get rid of the additional costs, additional constraints in the circuit and the result circuit, and we started thinking about why not to build a system where we can transform the code of the algorithm from the high level representation in C++ or Rust directly into the constraints on the data which algorithm works with. So we took the usual LLVM pipeline and designed basically a backend for that pipeline which works with the circuits. We have chosen the LLVM pipeline because that gives us ability to add new front ends if you want. We basically started with C++ front end because we write a lot in the C++. But the addition of the Rust front end took for us like a month or something like that, and that's basically it's basically a very nice feature we have, because the costs of the extension of our compiler, they're pretty low. Because it is an LLVM-based compiler, it installs the same way as the Clang or Rust-C compilers, and you can use it from your environment. You can install it in your regular environment or development environment and use it in your usual toolchain without changing anything. You can just write the C++ code and compile it with the CMake configuration make. It's the same for Rust. So I will show a simple example of how the transformation of the code representation looks like. Okay. So this is the C++ code, obviously, and we just call make as we usually do for the C++ code. We compile it into the intermediate internal representation, which looks like that. You can, I think it's pretty obvious how to match the code from the first slide to the second slide. Then you call the tool which we call assigner, which also can be installed in the pipeline, and which generates the circuit representation and the Plonk assignment table for the prover. And that does what he needs to do. It generates the constraints and the assignment table. Okay, I cannot show. So you see there is the code. It contained only three operations: add, addition, subtraction, and multiplication. And so we have only two constraints instead of like 200 or something for the zkVM pipeline. That's pretty effective, and that's basically what we wanted to achieve, and we achieved it through this way of compiling circuits. Because we wanted to build the zkBridges upon the compiler, and actually not only the zkBridges, but we started with zkBridges. Because of that, we wanted to reuse the logic we wrote on the compiler, the logic we wrote for the compiler. So we designed the Cryptography SDK, and so now we have two SDKs, basically, one for C++, one for Rust. The Rust one is kind of work in progress. The C++ is more stable. But both of them, they serve the same purpose, and they contain a lot of cryptography stuff. The proof system, I mean the Stark's the commitment schemes like LPC, FRI, KZG, and everything. The basic cryptography like hashes and ciphers, signature schemes and serialization, marshalling, everything like that. And all the stuff we have in the SDKs, it's pretty good optimized for the circuit backend. So you can, for example, take some commitment scheme from the SDK, write your own bridge, write your own proof system or using this commitment scheme, because you obviously will reuse one of the existing commitment schemes. And it will be pretty good optimized for the circuit backend, because you will just reuse the block components from other circuits. So this is basically how the whole pipeline looks like. You write the code on the SDK. It compiles through the front end, through the front end for this language. Then it compiles to the IR and to the backend. I have something like 2 minutes, so I will show the example of writing the Merkle tree circuit upon using the SDK upon the zkLVM compiler. I think most of people who are here know about the Merkle tree, but I'll anyway say some words about it. Merkle tree is a concept which is used in the base of the FRI commitment and the LPC commitment scheme, which are used for the zk snarks, and it's usually pretty huge because you can reduce the size of the proof using this concept, and we just wanted to show that you can easily compile it into the form of circuit, because if you can do it, you can do the recursive proofs, you can do the bridges. That's pretty important stuff. So that starts with includes from the SDK from the Crypto3 library, because this is a CPP example, so we use a CPP SDK. The declaration of the function, which takes an array of size 2 power 20. These are the leaves for the Merkle tree, which will be committed into the root value. And then you write like 20 arrays for each layer of the Merkle tree, but we obviously do not have this on the slide. We just you just need to imagine the whole bunch of arrays. And then you write the cycles to hash two nodes of data from the previous level to the node of the next layer, and that's basically all. You just wrote the Merkle tree. It just required two concepts from the SDK, and it doesn't require to know anything about the circuits, about how do they work. You just use the concept from the ready-to-use library and just write your stuff. This is the links for the core repo and for the docs. And now Ilya will tell about how to use the circuits, how to generate the proof and everything for that.
Yep. Hello, everyone. I'll talk about proof market as a proof generation infrastructure for decentralized projects. Mikhail explained why non-interactive proofs are important, how they can help to grow industry. Nikita shows a kind of easy way to generate the circuits, but the issue is that it's not enough, because you still need to actually generate proofs. And proof generation is costly, high-load process, especially for complex circuits. So that means that, first of all, you need powerful hardware, which works 24/7, and that's still not be enough, because, well, to achieve competitive proof generation timings, you still need to bring new optimizations in software, into hardware, into algorithms. And that's still not be enough, because even in this case, you cannot rely on centralized node. I mean, in this case, because centralized node affects liveness of the system, it affects throughput of the system, and actually you need a network of proof producers. Here we introduce proof market. Proof market is a centralized protocol that delegates proof generation process from proof demand applications to network of professional hardware operators. Basic workflow includes two roles, proof requester and proof producer. Proof requester wants to delegate proof generation process. For example, it could be zkBridge application may act as a proof requester. And as I said, proof producer is a professional proof generation hardware and software operator. The process includes several steps. First of all, both sides, proof requesters and proof producers, sends requests and proposals to the market. The matching algorithm continuously checks if there is a match between them. It takes into account proof producers' fees and expected proof generation time. If there is a match, then the request is assigned to proof producer, and proof producer starts generate proof. Then proof is ready, it's sent to proof market, there should be verified. If the proof is correct, then payment goes to proof producer, and well, proof goes to proof requester. Developers could add new circuits to proof market to let proof producer use them to generate proofs for them. And moreover, proof market is open to new proof system. It means that if you use Starks or Graph 16 implementation in your project, you still can integrate them into proof market and use this. Because basically it includes implement a verification functionality on proof market side. Let's look at developer workflow, application developer workflow here. Proof market toolchain is a repository that contains, first of all, proof generator and the CLI tools for communication with proof market. Firstly, developer should prepare a statement which is structured that contains circuit description, proving and verification keys for the circuits, and some extra information like short description, what the circuit actually does, type of proof system, URL to repository, all that stuff. And then it can just send JSON description of the circuit to the proof market. From now on, any proof producer can prepare proofs for this and get requests for this circuit. From the proof requester side, proof requester mainly interested in two things: to send request for a proof and actually get the generated proof. So to send requests, he just set the key or identifier of the circuit which he's interested in, and pass some costage they are willing to pay, and public input. From now on, proof market should find a proof producer who is ready to generate the proof, and proof producer generates proof, and proof requester just wait for this and then can download it via proof tools. Verification on external protocols works in the same way as usual as any call to any smart contracts on these systems. For now, for placeholder proof system, verification is available on StarkNet and Ethereum. In the future, we prepare verification modules on other protocols too. So, what to get in the full picture? Using this toolchain, we get a straightforward, lightweight way to prepare zk-based applications. To build zkBridge, you just need to write its logic in C++ or Rust, compile it, and send the circuit to proof market. And of course, that makes the whole process faster, cheaper, easier. But the most fascinating thing here, that's using this toolchain, even small teams or individual developers are able to build complex applications like zkRollups, Solana StarkNet bridge, trust without any trust in it. And it means that if individual developers are able to do this, it's opened a new wave of zk-based protocols, applications, solutions that can help to actually solve this computation and data scalability issues. That's all from my side. Thank you. And in general, that's all. Thank you, everyone. Any questions? Okay. No questions, I suppose. Oh, okay, yeah.
So for the proof market, is the vision for that decentralized or decentralized? And so
It's decentralized. It's decentralized. It's supposed to be, okay, for now it works as centralized node. We are in the process of moving into as a decentralized protocol. So in the, well, in the future, if you, oh, it's already, there's not our links, but if you subscribe, you'll find out the details on how to, how it will be done.
how do you enforce that the node actually took the public inputs, ran the proving algorithm, and
Well, verification procedures takes proof and public input and just, well, usual verification of production proof of the produced proof for, well, you just use the same public input as an input of verification algorithm for the proof. I'm not sure if I answered.
like, what if, like, let's say I'm trying to verify a CDCA signature inside the circuit, and what if the public input that I give is wrong? Let's say the proof will not be generated then, right? So that I can DOS the network.
Oh, got it, yeah. Well, in general, it's the question, it's more like a question for, okay, there's two phases of here. First one is public input verification. I mean, it cannot check that signatures are actually fine. Okay, it may check that signatures are actually fine. But yes, the first part is input verification. It's up to circuit developers, the one who builds the circuit, who transpile it, send it with, along with some rules of verification of any input. The second part, again, it's on more like on circuit developer side because, well, actually in most cases you can build a circuit which, in case if there is at least, if input goes through the basic verification checks, basic sanity checks, in this case circuit will work. Yep.
How do you match the prover, the requester, and provider? Is it per a specific algorithm or hardware-specific requirement?
Proof requester or proof producer?
Well, how do you match them?
Oh, how to match? Okay, yeah. The matching algorithm works as this decentralized, let's call it decentralized application. Okay, for now it's centralized, yes, we are in the middle of it. Basically, it's, well, it's more like any, you know, exchange-like matching algorithm for sets of bits and asks. Then you just, you need to find the, do you mean from technical side or from logical side, how much? I'm not sure that I understand. Okay, yeah. Well, from the technical side, it's similar to typical exchanges matching of bits and asks. From the, well, logical side, again, it's depends on the input from proof requester because proof requester could prioritize cost or proof generation time. And, well, basically, if it prioritizes cost, you just choose the cheapest proposal from proof generators, from proof producers.
The same hardware can run several algorithms, so to speak. Plum and other ZK.
It's the matching algorithm is not related to, well, ZK proof system at all. It's just usual matching algorithm. That's, yeah. I'm not sure. Well, yeah. As I said, it's not related to ZK. I mean, it just matches set of two tables, one with requests, one with proposals. Yeah. I'm not sure. Am I answered? Oh, okay. Okay, looks like that's all. Thanks, everyone.